Hello, folks. Welcome to Rational Science, the only site on the internet that does physics at all. Okay? We do physics here. What everybody else does, we have no idea whatsoever. They do something weird. Anyways, I'm going to be talking about Einstein's book today. And to put it in the right perspective, I'm going to start by reviewing what we did last week and then contrasting it against what Einstein proposed. Okay, how's that? And so let's start with that. This is what we did last week. Okay, we have these equations there. Really, it's one equation. I developed it and showed from a mathematical point of view how light is integrated with Newton's equation, really with the gravitational constant G. It's part of that. Okay, which is part of Newton's force equation, which is not a force equation, it's a tension equation, and tension is not a force. Okay, that's essentially the message that I gave out the other day. Okay, so we start there by saying that the electromagnetic wave was confused. In other words, a rope was confused for an electromagnetic wave. They thought that what was in that region was a transverse wave moving from left to right. And what you really have is a torsion of a rope which is spinning, torquing in situ. Okay, that's what we're proposing in exchange for the electromagnetic wave. A wave is a concept. A rope is a physical object. So we're talking about two twined threads. Thread is an object. Fields are not objects. Fields are a bunch of numbers. And so mathematicians are doing physics, physical interpretations with concepts. That's where the irrationality of mathematical physics comes in. Okay, that's what we're proposing. We should be wiping all that away and replacing it with objects. If you're going to give a physical interpretation, use objects. Now, if you want to do math, that's something different. Okay, here we're talking about physical interpretation. We're talking about physics, not math. Okay, even though you see equations there, what we're doing here is really trying to explain what the equations represent in physical terms. Okay, so he has, or the mathematical world today has force equals G, the gravitational constant G, mass divided by distance squared. Really, they put radius. We're going to replace that with distance, and there's a reason for that. Anyways, there you have the gravitational constant G. The value there, very strange units, meter cubed over second squared, kilogram squared, whatever that means. Kilograms times meters cubed, by the way. So whatever that means, right? So we're going to put that into the force equation, right? And so first we need to figure out what that G stands for. And there you have it. Those are the values. We're saying that the gravitational constant G represents velocity of light squared, or speed of light squared, right? The mass of the hydrogen atom, both of those are constants. And so, yes, since G is a constant, it better be made of constants, right? And what's left over is the 0.44 meter over kilogram squared. What is that? Well, when we integrate the kilogram squared with the hydrogen atom, you get Mach's principle. And here, I'll just show you a quick picture of that. If you only have two atoms in the universe, right, bound by a rope, not by a wave, transverse wave, no, it's a rope that's torquing in situ. There are only certain motions that it can do that you can imagine, assuming those were the only two objects in the universe and assuming they're moving, right? Okay, so you would think that they're twirling in such a way, like the first one there, where they push each other away, right? When they spin in such a way that atoms are going outwards, right? And that's the axis parallel to gravity. When an astronaut falls to Earth, every atom of his body is bound to every atom on Earth, and so he's falling, right, in a straight line because the ropes fan out, so he's falling in a straight line, and that's what that imitates. It's the parallel direction to gravity. The other one means that, it can twirl in such a way that it's against the pull of gravity, right? And so that's got to be a squared motion, right? Because it's a circle. It's perpendicular to the parallel direction of gravity. And so those are that's why it's in the denominator. And that's why we have what we call Mach's principle. Means that this object can move twirling around, right? And also twirling in such a way that it oscillates around, perpendicular to the direction of gravity. And so those three motions that it can do, we call Mach's principle. Do we need to have it move? No. But what we're saying essentially is that if you have an atom, any atom in the universe, at any point in time, it's being pulled by every atom in the universe, or there's a tension between that atom and every atom in the universe in three directions. One is the direction of gravity, and the others take away from gravity because they're sideways. Okay, that's what we're saying for any atom. Okay, and so yeah, that's Mach's principle. And once we factor Mach's principle and light, as you can see, we replace the little c there with frequency times wavelength. That's the velocity of light. 300,000 kilometers per second is a constant. It's made of frequency and wavelength. Now, people say, well, you can have any wave, like for wave, you can use velocity. You can put a little v there, which is what they used to do. But see, that's for any wave except light. Okay? For light, it's a constant. And so for any other wave, you can make it go faster by increasing both the frequency and the wavelength. Okay? You can't do that with light. With light, if frequency goes up, wavelength goes down, and vice versa, because you have to maintain the constant speed, 300,000 kilometers per second. Okay? So yeah, we put frequency times wavelength square there, and what's left over is that 0.44 meters, and you say, well, what the hell is that? Well, we're saying that that's the amplitude. If you take any rope, okay, really any wave, you can use this for the wave as well. You take any rope, you have number of links, frequency, link length, wavelength, right? And you have the amplitude, this, okay? The amplitude of the wave. Those are the three parameters of a wave. We're saying that meter, 0.44 meters, is the amplitude, the universal amplitude of a wave, average amplitude. And I explained last week why that number is 0.44 meters. In other words, almost half a meter. You would think that it should be a lot thinner, but, just check the video of last week and you'll find out why. Anyways, those are the values for light. The light component is average universal amplitude, frequency, and wavelength. That's the light part that's in the gravitational constant G. And the other one is the matter part, you could say, the Mach's principle. It involves the atoms themselves, okay? And yeah, you can replace that with energy and matter, which are the words that the mathematicians like to use. And that's essentially what comprises the gravitational constant G. Now, the next step is to put that G inside the force equation, right? Force is really weight. What we're looking at here is weight. And weight is location specific. Weight is not a dynamic concept as everybody thinks. Everybody says, well, I'm sitting or pushing down, I'm pressing down pressure, right, on the scale. No, you're not. No, you're not. Forget the scale. Throw the scale away. Don't use any numbers, okay? Anywhere around the Earth, I don't care where you are in space, right? Any astronaut has weight at any given location. And at one location, he has one weight, becomes closer to the Earth, he weighs more, just moves an inch, he's already got changed locations. At that location, if we took a snapshot, we already have weight. And you say, how can you put weight in a snapshot? And that's what we do. We put weight in a snapshot because it's the number of ropes converging upon each atom at that location. It's the number of ropes. That's what weight is, number of ropes, independent ropes. Far away, all the ropes come together. They act as one effective rope. Close by, they widen, they fan out. And now you have many ropes acting independently. And that's weight, okay? The number of ropes. That's what weight is. It is a static concept. So if it's a static concept, remember, on each rope, there's no pull. It's not an elastic rope, Okay, people think the ropes are pulling. No, they're not. There's tension. Okay, tension is a static concept. Nobody wins the tug of war. The atoms slide through the ropes because they're made out of the same thread that the rope is made. So it eats into the rope as the threads go around it. Okay, that's why you don't add the speed of the atom, whatever atom, right, the source, to the velocity of light. Light always twirls at the same little c, and little c is a measure of the tension on the rope universally. Okay. Anyways, the point here is that we have tension, and that's what weight is. A tension is a static concept. And again, you can see we replace that at the bottom with tension equals energy times matter, and then the mass distance squared. Okay, so that's what we propose. Okay, that's the theory, and in other words, a physical interpretation of Newton's equation. And it's up to you to, do your own thinking, reach your own conclusion. Don't let anybody else do the thinking for you. Certainly you will not allow someone else to do the loving for you. Okay, so don't let someone else do the thinking for you as well. Have the kids for you and everything, Cuckoo, right? Okay, so how does that differ from good old Einstein? Well, we have a little difference there. You can see the ropes from an asteroid that's falling to Earth. As it comes closer, the ropes fan out. That's what we're showing there, okay? And that is the acceleration of gravity. You have more and more effective ropes, as we call them, independent acting ropes. And that's totally different than what Einstein proposes. Einstein says, look, because they do it all mathematically, right? They say, well, we have all this mass. We don't have a sun. We don't have the Earth. We have a mass, a big mass and a little mass. Okay, so we have masses of masses. Okay, we have a big mass, and it weighs down what looks like a canvas, like a trampoline fishnet. That's what it looks like to me. I mean, objectively, that's what is in front of me. Okay, I don't know about your eyes, but that's what I see. Okay, so we have this weighing down of the canvas, right, of these number lines, because they call them dimensions, they call them coordinates, vectors. No, those are number lines. Dimensions is what you have in physics, length, width, and height. Coordinates is what you have in physics. Vectors are what you have in physics. But in mathematics, they have none of those three. They only have number lines, okay? It's a line that's got a bunch of numbers with different values. That's what they have, and that's what they illustrate there. They're illustrating number lines. And what Einstein's going to do, at least that's what he proposed, is that any massive object like the sun, right, weighs down with mass. It's the mass. See, he doesn't show any contact between the sun and the fishnet. Okay, there's no physical contact. He's just saying, look, the mass of the sun somehow weighs it downwards in this case, right? I've never seen it illustrated upwards either, by the way. Turn it upside down maybe, right? So it weighs it down. It creates a depression, right? A little bowl. And what you have is the Earth cannot fly out of the solar system because it's got this wall, this curved wall. It's rolling around a bowl. So that means that the skin of the Earth is pressing down against this bowl, and somehow, for some reason, we don't get squashed against it. I mean, if the edge of the Earth, right, where I'm at right now, is pushing against this depression in space-time, right, and it's physical enough to prevent the Earth from flying out, I should be squashed. And thank God I'm not. I don't know about you, but I'm not. Okay, and essentially this is what they're illustrating. Here you have, you've seen those motorcycle guys that are in a cage? That's essentially the mechanism they're proposing. Here it is. Okay, you got these people running around in their motorcycles, right? And why? Because the cage is curved, right? And that's essentially the mechanism they're proposing. And this is what we have today. This is the mechanism. Okay. So the reason the Earth doesn't fly out of the solar system is because there's a wall of something called space-time, which is really a concept because it's number lines and they're curved. They're curved not because you physically push them down, but because, mass somehow curves the number line. It's all mathematical, right? That's the interpretation. And that's the reason the Earth doesn't fly out of the solar system. That's the explanation. The motorcycle in a cage mechanism, okay? Okay, so here's one fellow that illustrates that, just in case. Most of you know him. His name is Ryan Green, and let's hear him say it to you, okay? Here's from the horse's mouth, okay? Here it is.
The ball travels along an indentation in the fabric that the heavier object creates. And this, Einstein realized, is how gravity actually works. It's the warping of space-time caused by the objects within it. In other words, gravity is the shape of space-time itself. The moon is kept in orbit not because it's pulled to the Earth by some mysterious force, but rather because it rolls along a curve in the space-time fabric that the Earth creates.
Okay, so you've got it illustrated. There should be what was objectively coming out of the screen into your eyes, and you hear Brian Greene telling you what they believe, and he says it with so much certainty. He's sure of it. That's been proven. It's a done deal. You can't even dispute it anymore. And so when you question that and say, look, it's irrational what you propose, you're saying that number lines are being warped by something called mass, and the number lines, are also a concept. That's when they say, well, you're talking, first of all, don't take the analogy so literally. And then they say, well, that's philosophy anyways, ontology, semantics. What we do is numbers. And we can't put those numbers into ordinary speech, into qualitative expressions, right? We can't put it in ordinary speech. And so you say, well, who can? And they say, well, Father Universe, Mother Nature, they don't have to really conform to our way of thinking. What they're telling you in your face is that the mathematicians are the interpreters of Father Universe and Mother Nature, like, the priests of old used to interpret the Bible for you, and the ignorant masses who did not know how to read or write, they had to depend on this priest, on this monk or whatever, to tell them what the Bible said, because, they said, well, this guy's studied at the seminary, he's a bright guy, he's an intelligent guy, I'm so dumb, and so they had to believe him. And the same thing happens today. You have these mathematicians, they do all these equations, and people say, oh, look at all those equations these people know. Who knows all those hieroglyphics? And so they get all, they like to create icons. They like to make celebrity out of these people because look all the stuff that he knows. And it turns out he gives you an irrational explanation, like saying, the language of Father Universe is mathematics. We know the language, and here it is. This is what he's saying to us and to you, through us to you. And when you question, say, well, hold it. You represent Father Universe? You're the spokesperson for Father Universe? I mean, one thing is for you to tell me that the equations say something. Another thing is for you to interpret that and give me a physical interpretation. And I'll give you an example. Let's say, because people say, well, technology works, so they must be right. Computers work. Why? Because quantum is right. And GPS works because why? Relativity is correct. But see, that's like saying, again, let's assume you put a business, right? And you say, hey, I'm going to make some money. I'm going to put a junkyard, okay? And I'm going to use these big magnets to pull cars up and organize them in such a way that I'm going to have the best junkyard in the country, okay? Someone comes to you and says, well, hold it, here you have this big magnet. It's lifting up the cars. How does it do it? Oh, easy. We have all these angels, and they go back and forth between the magnet and the cars, and they pull the cars up. And you say, well, that sounds irrational. Well, technology wouldn't work. My junkyard wouldn't work if the angels did not exist. And that's more or less the situation here. One thing is the mathematics and the fact that technology works because it was designed or it was developed through trial and error. Another thing is for these people to tell you what a magnetic field is or how the atom really works at that, invisible region of the world where, the electrons apparently do their quantum jump and whatever. So they don't have any idea what gravity is. They don't have any idea what light is, but they claim to speak for Father Universe because their equations say something and they're interpreting those equations. So you got to be careful with letting them put these ideas in your mind thinking that, oh, they're so intelligent, they know all that math, so they must be right. It doesn't follow. Okay? In fact, they have the most irrational nonsense coming out of mathematical physics that you can imagine. And so to say that because they know math, they can interpret how this universe works, that's a big jump right there. Okay. Anyways, here you have good old Einstein and what happened with him. Well, it's important to know because they don't tell the public this stuff, okay? And that is that Einstein became an atheist in general relativity at the end of his life. He didn't believe in quantum mechanics, and at the end of his life, he stopped believing in general relativity, relativity in general, special relativity, the whole works. He stopped believing in the physics that had evolved from his own ideas. And they punished him. They punished him by, making him a hero. That's the way they punished him. He was, his name was used as a synonym of intelligence. And they said they continued with that. And he objected to a lot of stuff. He did not believe in Big Bang. He did not, singularities, right? He did not believe in black holes for the same reason. He wanted to do physics with a little bit of object. He thought there was really something in there. And today they're doing it with nothing, with concepts. And he didn't like that. He knew that was counterintuitive. So he didn't like a lot of stuff that came out. He didn't believe in gravity waves. He wrote a paper, 2 papers, I think, on that. Nathan Rosen, who was part of that EPR, the Einstein-Podolsky-Rosen. Nathan Rosen wrote a paper talking about Einstein's notion of the gravity waves, why he rejected them. And so he didn't believe in black holes, Big Bang, gravity waves, a lot of that stuff that is being, attributed to Einstein. You see all these articles, they put the name Einstein in there and people get the idea, the wrong idea that, oh, Einstein believed in all this stuff. Absolutely not. They're confusing, the equations that Einstein developed, his interpretation of those equations with what his disciples, his followers, eventually did with all that. And so here, towards the end of his life, this is what Einstein had to say about relativity, why he didn't believe in all that garbage. Okay, and here it is. I have become an obstinate heretic in the eyes of my colleagues. He was working at Princeton, right? Princeton Advanced Studies. And he was put into a corner, where he collected cobwebs, and nobody paid any attention to him, partly because he did not believe in quantum. And so he wrote another letter, this one to Bohr. He says, I'm generally regarded as a sort of petrified object, rendered blind and deaf by the years. And the last one is the good one, to Michel Bezos. And he said, all these 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. I consider it quite possible that physics cannot be based on the field concept. Remember, he created the field equations, right? And he says it cannot be based on a field concept, in other words, on continuous structures. In that case, nothing remains of my entire castle in the air, gravitation theory included, and of the rest of modern physics. And so that was his slap in the face to the mathematicians, and essentially he stuck his tongue out at them. He said, oh, you dumb Dummkopfs, right? You believe in all the nonsense that I created? Yeah, forget it. You're wasting your time. So he laughed at the math club, okay? Okay, so that's how his life ended. He never discovered how this universe works. He did not discover the grand unified theory, which he was searching. toward the end of his life. He was looking for an equation, and it's got relatively little to do with an equation. It's got to do with interpretation, a physical interpretation, something that mediates both light and gravity, and that is a rope. That's the only thing that can do both. Okay, that's what we propose here. So one fellow tells me, he wrote in Quora, right? And he says the following: what causes gravitational forces to exist? And this is how, that was the question. This is what he answers. He says, answer that and you can have a PhD from pretty well anywhere and you would likely get a Nobel as a bonus. I put that in different color and you'll see why at the end there. Short answer, haven't a clue. In other words, no one knows, right? Even if we did have an answer, it would only be in terms of some more fundamental process of nature, and you would then get to ask why that exists. In other words, you would keep asking why and why and why, right? Physics and science is about what? Asking how things in nature behave and describing, mathematically describing. Math can only describe that behavior. And then he goes in the end, I like that, and he says, why is the realm of religions, right? Philosophy, opinions, metaphysics, opinions, right? Religion, if you subscribe to them. So what this fellow is saying, which is the way a lot of people think out there, as I found out, he's saying the following. He says, if the question is what causes gravitational forces to exist, he's saying no one knows the answer. Okay, that's the first answer he gives. Then he says, if you know the answer, you get a Nobel. Okay, that's what he was saying, right? And then he says, but if you can answer the question, you will only get more why questions, right? One question after another. Why is it? In other words, why did the hand push the box? Well, because, I used my hand and I pushed it. Oh, but what pushed the hand? Well, it was my wrist. Well, what pushed the wrist? Well, it was my elbow. And what pushed my elbow? Well, it was my shoulder. So he's saying that it's an infinite regress where everybody just keeps asking, well, why this and why that and why that and why that? And so, no. The way it works in physics is, you're in front of the judge and the judge says, how did the window break? And the mathematician would say, well, there was this mass, okay? And it had so much energy, it went through with so much force against the window, and the window, the tension was not sufficiently strong for it to resist the force. That's how a mathematician would answer a question of physics. And no, you go with that to a judge, he puts you in prison, he gives you a life sentence. That's what maybe sends you to the electric chair. No, the way it works in physics is a rock went through the window. That's how the window broke. Okay? Very simple, very baby-like, kindergarten-like. Mechanisms are baby stuff. Physics is for kids. Math, you got to go to college, if you want to learn it to great degrees. But physics, any person should understand physics because it's the way Father Universe works, Mother Nature, they work with objects. They move one atom to another location all day long. That's all they do in the universe. For every atom in the universe, it just moves to a new location. From frame to frame to frame in the universal movie. That's it. There's nothing more. And so to say that, the mass went through at such force through the window, now, a rock broke the window, went through the window. That's how we do it in physics. That's the mechanism of how the glass ended up on the floor. Period. We're done. Then you can talk about other mechanisms, what forced the rock, that's a separate mechanism. But we've answered the question. That's how you do it in front of a judge. Otherwise, he sentence you either to death or life sentence, right? But the contradiction is here. He says, if you know the answer, you get a Nobel. And at the end, he says, which contradicts his first statement there, that you get a Nobel for answering a why question. He says, if you answer the question, you get a Nobel. Then he says, oh, but that's religion. And since when do they give Nobel Prizes for answering why questions, answering questions of religion? Since when was religion part of the Nobel Prize? So they live with all these contradictions. And what it comes down is to a statement made by this gentleman. His name was Émile Bois-Reymond. Okay, he was German, and sounds more like French, really, to me. And he said, "Ignoramus et ignorabimus," okay, which means we do not know and we shall not know. Okay, and that's more or less the philosophy of so many people out there. We don't know. We don't know anything. There's no way we can understand the universe. It's so infinite, we'll never figure it out, and blah, blah, blah. And all these scientists, they think they're so smart, but they'll never answer the question. All we can do is work towards an answer or try to figure out more and more as we go along. So they have this ridiculous philosophy that science is a process of investigation, of searching, but never finding. Okay, because we'll never figure it out. Because the universe is infinite, that means knowledge is infinite, God is infinite, so is space-time infinite, everything is infinite, and we cannot understand infinity, so let's forget about it. Let's just keep doing one step at a time until we figure things out. And so, so they have this idea that this fellow proposed, known as the limits of science. And no, we have a totally different view here. Humans are intelligent enough, so intelligent that if God himself, omnipotent and omniscience, right? He comes down and sits right next to me or to anybody on earth that more or less has a brain, and he explains how this universe works. Every person should be able to understand what God is telling you. Okay, so if you have this being that knows everything, and he explains to you how this universe works, you should be able to understand it. Now, no one can understand space-time. No one can understand, a particle being at two places at once and all this nonsense that came out of relativity and quantum mechanics. Nobody can understand that. And so people say, well, we'll never understand it. No, it's because these people are telling you that they're the representatives of God, of Father Universe, of the devil, or who knows who out there. They say they know everything, but at the same time, they say, well, we don't know nothing. What do you mean you know nothing? You know everything or you know nothing? Which one is it? They say, well, we know everything because the math is the language of Father Universe, but we cannot make sense of it in regular language, in qualitative terms. And that's the pitch, that's the sales pitch that they give you. Okay, and so here we have someone who tells us that what these people are doing is math and not physics. And people say, well, it's mathematical physics, right? It's like one discipline. No. Math is math, physics is physics, and never the twain shall meet. Okay? Never will those two meet. Math has nothing to do with physics at all. We don't use math in physics. What they've done is since the 17th century is tell us that math is the language of physics. In fact, Galileo said that you need math equations and you need experiments. We don't use either one in physics. We don't present experiments in physics. You say, Bill, what are you saying? That we don't use experiments? Yeah, in physics, we do not do experiments. That's for gophers. You send a technician or the operator and he does the experiment for you. The engineer, the scientist, right? These people, they're at their desks and all they do all day is think. They think until they thunk. And their job is not to do experiments or do equations. What they do is they come to a conference and they explain an experiment. The job of a physicist is not to do, but to explain the cause of an experiment. And yeah, you can't do that with equations. That's why math has nothing to do with physics, nor physics with math. Okay? And so here we have good old Richard Feynman, Dick Feynman. And he says, physics is not mathematics, and mathematics is not physics. You got to listen to this fellow, okay? And here he goes. Let me show you what he said, okay? Here he goes. Listen carefully.
Physics is not mathematics, and mathematics is not physics. The mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about. Now, the physicist is always interested in a special case. You have to have some understanding of the connection of the words with the real world. He's talking about something. When you know what it is you're talking about, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. The mathematical rigor of great precision is not very useful in the physics.
Okay, so no, math is not physics and physics is not math, but people don't understand that. They think they're equated. You know, that one is the same thing as the other. And that's where we have a problem, because we don't have any physical interpretations today, no qualitative explanations. We have no idea what this, and by we, I mean the mathematical establishment. They have no idea what this universe is. They misconceived it completely, and they're not even close. That's one issue. And then they don't have any idea how it works. And they're still searching for basic things like gravity. And you say, well, gravity is so difficult. It's so incomprehensible. Here's gravity. Let me show you how easy this thing is, okay? Here, I got this little straw. It weighs very little, so I like to use this instead of my pencils. Okay, I let go of it. There it goes. Okay? That's gravity. That's the only experiment you ever needed to do if you wanted to do an experiment. Now we have to explain it. That's what we do in physics. And how difficult can this be? You have the straw, right? And you have the earth. Those are the only two objects involved here. Okay? Take the air away, all that stuff, because this can work anywhere. It can work even on the moon at a different rate, but still work on the moon. And so you have this object. It just falls, and it's the earth and the straw. How difficult can that be? And the only reason they never figured it out that there are invisible, intangible objects, mediators, agents, that we cannot see or touch, that bind every atom of the straw to every atom on Earth. And that's the only reason. I mean, if we could see them, you'd say, oh, how stupid, it's so easy. You know, it's like seeing the magic trick the magician did on stage. If you see how he did it, you say, well, it's so stupid. But until you know how he did the trick, it's really magic. You say, how did he do that? He cut the lady in half, she came out alive? Turns out it's a trick, but you don't know how the trick is done. And this is the same thing. You know, and hopefully there's something here that we cannot see or touch. So whoever proposes a theory of gravity had better make his mediators invisible and intangible. You know, like the neutrinos. Neutrinos are invisible and intangible. They created them out of thin air with a magic wand. Okay, that's what's happening. And yeah, we have all these notions that, or everybody out there seems to have this notion that objects don't go through objects, and there are no such thing as invisible, intangible objects. And yes, there are. And until you wrap your head around that, until you come to grips with that reality, that Mother Nature uses invisible, intangible mediators to do gravity and light, until you grasp that, you're never going to figure out what this universe is or how it works. You have to get that. And any theory had better make their mediators invisible and intangible. And the other thing I like to say about that is there is no theory that does not have invisible, intangible mediators that go right through each other. Objects that go right through each other. And people say, you're crazy, my theory doesn't do that. All theories do that. The problem is no one has pondered that or figured that out in their theory. They've never embodied that in their theory. They never thought about it. They just keep doing their theory and say, oh, it's done by density, it's done by particles or waves or whatever. But they never said, well, do the waves go through each other? Do particles go through each other? They never asked those questions. And part of that is because they're using concepts. You know, using the field, they're using the energy, force. They're using all these concepts to do their physical interpretations, but they never ask the question, does an energy go through another energy? Does a wave go through another wave? does a particle go through another particle? And you say, well, it's a little ball. How does a ball go through a ball? Well, it turns into a number. That's how it is, because the particles of mathematical physics are not particles. The word particle is in there. It's very misleading because they're talking about numbers. They're talking about quantities, and people don't understand that. Okay, and here you have Beecham. He tells you, Jim Beecham, and he will tell you that, yeah, physics does deal with physical interpretations. A lot of mathematicians believe that it's not, that what they do is just numbers, equations, and when they're asked to bring it into the real world, they'll give you this irrational explanation, but they'll say, well, that's philosophy, that's ontology, it's metaphysics. So they dismiss it as, don't ask me that question because that's not in our job description, right? And Beecham tells you here, listen to him, he's a mathematical physicist, and he'll tell you right in your face.
What causes gravity? So physics, as you know, this is the type of question, what causes gravity? This is the type of question that keeps physicists up at night. Because physics is, among other things, as you know, the search for mechanisms, the reasons or explanations for why certain things happen the way they do.
So, do physicists, or are they interested in physical interpretations? Well, the answer is yes. But they stopped doing that, like Richard Feynman said once. He said, because they've given up on that. They cannot make sense of the universe, so they've given up on physical interpretations. And he said that in the 60s. Here we are 60 years later, and so people today say, well, yes, physical interpretation is not part of physics. All we do is math. And people accept those answers today. Okay, so here we have Gödel, and he'll tell you in his book, the one I'm going to talk about next, and he says why he wrote that book. He says that in the preface, right? It says the special relativity, that's the name of the book, special relativity, the special and the general theory, okay, began as a short paper and was eventually published as a book written by Albert Einstein explaining the theory of gravity. And this is what he says in the preface, okay? He says, an exact insight into the theory of relativity, right, to those readers who, from a general scientific and philosophical point of view, are interested in the theory, meaning the explanation, right, the mechanism, right, the causes, but who are not conversant with mathematical apparatus of theoretical physics. So he's going to explain why the underpinning of the theory. He's trying to explain to you how they came up with this notion of warped time, right? He calls it space-time. I like to focus on the word time because that's so weird to say that time is warped. And so, he's going to explain to you why, how they came up with that. And it's important to understand that he was not the only guy involved, okay? Because the only name that has survived to us since the late 19th century, beginning of the 20th century, really, was Einstein. Nobody knows anybody else. You ask someone on the street, who was Oliver Heaviside? Or who was... some people don't even know Maxwell. There was one guy that stood in Scotland in front of the statue that they have of James Maxwell. And here you have all these people walking around there, going to their jobs and so on. And he stopped people and said, who's that statue there? I said, I don't know. And when he said, well, that's James Maxwell, it's like, okay, so who's he? And these were the Scots. So, the only name that has survived is Einstein, and that is a problem. That is a problem. Okay, let's start with the book, but before we can get to the book, we have to put it in the right context. In other words, Einstein was not only the only person involved with the development of relativity in general, special, and later on general relativity, but he was not the only fellow, but none of those names survive to this day. And it turns out that a lot of these ideas came when he was a kid, when he was not even a teenager in some cases. So I like to synthesize it with this picture here, if you allow me to do that. Okay, 1887, Michelson and Morley, they run their test on ether. They were trying to prove whether the ether existed or not, because a lot of or just every mathematician really in the 19th century believed there was an ether, and they were just trying to show how that ether behaved or what properties it had. And so they ran a test that proved to many mathematicians that there was no ether. Okay, and this shocked a lot of people because there was a fight after that on whether there was an ether or not, right? And even people today say, no, there is an ether, and Michelson and Morley just did their experiment wrong, or got the wrong conclusion or whatever. But you can see how old Einstein was. He was 8 years old. He was born in 1879. He was 8 years old when Michelson and Morley ran their experiment. Heaviside, in fact, before Heaviside, really, I got to put this fellow up there. I'll put him in there for a second. His name is Waldemar Voigt. Okay, and Voigt came up with this special notation, which we have the new notation these days, which is that little factor there, which is the v squared over c squared. Okay, he was trying to answer the Michelson-Morley experiment, and as far as I could trace it back, he's the first person to come up with this. It's confirmed by two people, at least, in those days. One is Minkowski, who was Einstein's teacher at one point in time, and also by Lorentz. These people confirmed that Voigt was the guy who came up with that equation. And that little v squared over c squared, that factor there, right, that's a very, very important factor because it underpins all of special relativity. Special relativity would not work without that v squared over c squared, and Einstein was not the guy that came up with that. Okay, he came up with that in 1887, again, to answer the Michelson-Morley experiment. Heaviside, the guy who comes up with the length contraction. Fitzgerald and Lorentz later on, right? Both of them working kind of independently. Apparently, Lorentz was not aware of Fitzgerald's complete work, and so today it's called the Lorentz-Fitzgerald or Fitzgerald-Lorentz equation. And they essentially came up with, this time dilation notion, and also of the shortening of sticks and so on. And it's Poincaré, French guy, when Einstein is only 19 years old, he was still in school, right? Who really comes up with the discovery of special relativity. But these fellows, nobody knows them anymore. I mean, if you study some physics out there, you'll find their names. But if you ask the public, go to China, right, and ask a Chinese on the streets, Chinaman, if he knows who Lorentz is or Poincaré, they won't. Ask him about Einstein. Say, oh, Einstein, yeah, I know who he is. Even though it's not part of their culture, he didn't form part of their culture. But all these people went away. Nobody knows them anymore, right? And Einstein took the credit for all their work, even though Einstein came years later and, used their ideas, put them together. So what did Einstein contribute? Why did he become famous? Or why was he, how did he emerge in this world? Well, he's the guy who said there is no ether, allegedly. Allegedly. I'm going to emphasize that. Allegedly said there is no ether. That's what he was arguing for, okay? But not completely, okay? So what is Einstein's ether? It's important to understand, what he was saying here as far as the ether is concerned. And here's a synthesis of what he said in the first 20 years of the 20th century, okay? This is more or less a synthesis of how he saw the ether. And in general, right, how he saw this space-time thingy out there. One can actually speak about a new ether. Okay? He's talking about a new ether, but one may not speak of motion in relation to that ether. Special relativity, it took away the last mechanical property of the ether, immobility. Special relativity does not rule out the ether. Why did he have to say that? Because everybody and their mother believed in the ether. And so he was fighting the entire mathematical establishment of those days. You had people like Poincaré and Lorentz. They both believed in the ether. They were trying accommodate the ether somehow in Michelson-Morley's experiment, in their conclusion. They say, no, there is an ether. We just need to interpret that experiment, those experiments, they did a couple of them. We need to reinterpret those experiments under the ether hypothesis. Okay? And Einstein's saying, look, special relativity does not rule it out, because he had to please the establishment and he wanted to get ahead in his career, right? But then he says, in general relativity, physical properties are attributed to space. Okay, so now he's taking nothing. Space is nothing. There's nothing called space. What is nothing? It's that which has no shape. It's the opposite of something, which is that which has shape. So now we have a definition for something and nothing. Space is nothing. But he gives physical properties to this nothingness, okay? But no substance or state of motion can be attributed to that ether. So it's a something that is not a substance, whatever that is, because a something is a substance. They're both synonyms in physics. It's that which has shape. And space is that which doesn't have shape. Therefore, it doesn't have any properties because it's not a thing. It's not an object. And if you believe otherwise, all we want you to do is to draw it. Show us a picture of space and identify the contrast, whatever gives it contour, okay? The object that's behind space. That's what you got to do, okay? And it says, but no substance or state of motion can be attributed to that ether. So we have this non-substance, which has physical properties, physical being a synonym of substance, right? And he says it doesn't move, right? Because it moves with respect to what? Would have to move as a whole with respect to something else. The ether became four-dimensional. In other words, he's saying that ether and space-time are synonyms. That's what Einstein is saying. But space-time is not part of special relativity. Space-time is part of general relativity. Space-time, special relativity is general relativity without gravity. In other words, it's what the flat earthers like. You know, it's a flatland. Flatland, you cannot fall downwards because there is no downward, there is no gravity. And so what Einstein was saying is, we can't use the ether really in special relativity, even though it does have properties, right? But we absolutely equate it with four-dimensional space-time. And he says the ether of special relativity is still absolute because matter is affected by the properties of the ether. But listen to this. But the ether is not affected by the presence of matter. So we have a one-way touch. The ether touches the thing, but the thing does not touch the ether. And it reminds me of the movie Ghost, where the ghost, he comes in, he does all of these magic tricks. He comes in and out. He can touch things when he wants to, when it helps the movie, the plot of the movie. But otherwise, he can go through things. And here you get some pictures of this ghost. Okay, here it is. Okay, so what Einstein did, create one-way touch. The ghost touches you, but you cannot touch the ghost. That's so weird, you try to touch the ghost, you can, but the ghost can touch you. And that's kind of magical, and that's what he wanted to say essentially here. He's saying his ether, as far as special relativity is concerned, is one-way touch. So he invented one-way touch, and that's one of the things that, the mathematicians didn't like too much of those days, the establishment, right? And he says that this asymmetry was solved within general relativity. Did he solve it? Well, he says because matter is influenced by the ether just as matter influences structure of the ether. And he had to do that. Why? Because he's going to say, what are the field equations? The field equations say that when Mercury takes a step forward, it bends space-time. because it bent space-time. Space-time now hits back and changes the itinerary of Mercury. That's what he's saying. So yeah, there is a mutual touch. But in special relativity, he says, well, we don't really need it, but space does still have some properties. And he's going to talk about the properties and not about space itself as an object. That's where the cheating comes in, okay? It says, the only similarity of this relativistic ether concept with the classical ether models lies in the presence of physical properties in space. So he's going to give some physical properties to nothing. Space is nothing. Space is that which has no shape, but it's got physical properties. It's not a substance, but it can hit you in the face. That's what he's saying. And says, no substance and no state of motion can be attributed to that new ether. Okay? So we have this strange ether that Einstein proposed. And it turns out no mathematician really bought into it. Nobody paid any attention to Einstein's ether, and it gradually faded away. Mathematicians had no use for the ether because they were going to do everything with abstraction, with mathematics, with equations, with numbers, right? But we reach today, and we have this Nobel Prize winner. His name is Robert Laughlin, and he says, the modern concept of the vacuum of space, right? Confirmed every day by experiment, is a relativistic ether. But we do not call it this because it is taboo. Yeah, they never got rid of the ether. They never were able to explain what's out there. And they use all these different terms like virtual particles. Here's one example, virtual particles, right? And they have all these particles that are out there, and they live only for a split second in our world to make the equations come out right. And they immediately disappear. Then they are unmeasurable, right? And here this is how they illustrate them, okay? And so you have all these virtual particles, and that's the ether. But they don't call it that because it's taboo. And what is space-time? Well, space-time, again, is also an ether. And you say, what do you mean it's an ether? Yeah, because space-time is defined, or better yet, let's define it in reverse. An event is defined as a point in space-time. That means space-time is made of all these points, all these events that make up space-time. So it's a circular argument, you know? Events make up space-time. What is space-time? A bunch of events. Okay, that's what it is. It's a circular definition, a notion. And what are all these points? Well, particles. And what are all these particles? The background, you know, the background radiation, bunch of particles in the background. It's an ether. It's an ether theory, but they're not going to say that. But Einstein said it. Is ether with this four-dimensional. And of course, mathematicians today don't want to relate the word ether with their four-dimensional space-time. It's taboo, okay? So keep that in mind. But when you give a physical interpretation, you got to have some kind of background there, and that's where the problem comes in. That's when they say, well, that's ontology, that's belief, that's philosophy, metaphysics, who knows what. Okay, so what happened was that something was happening during the days that Einstein was growing up. And that's in 1905, he makes his annus mirabilis, call it the anus mirabilis. He came up with 4 papers, and 2 of those are of some significance. One he won the Nobel Prize for, which is the photoelectric effect. The other one is the one that gives rise to special relativity, which he kind of borrowed from Poincaré, okay, the French guy. Okay, so what's the issue? The issue is that you've got World War I, 1914, and at the time he separated from his wife, Mileva, a Serbian gal. They had 2 kids. She took the kids with her. By 1919, 5 years later, partly surely because of the war, they finally divorced. So 1919 was a great year for Einstein, or a significant year, because he got divorced. He got married again with his cousin, and that's when Arthur Eddington blesses his theory, and he becomes a household name around the world. Okay, and so 1919, you know, because Einstein had predicted that light curves around massive objects such as the sun, and Arthur Eddington had an expedition, which really was not proposed by him, was proposed by another British guy, but he got the credit for it. He says, hey, I proved Einstein right. And that's when he became a household name. Here you have a couple papers of the age. Okay, this is from the Washington Times, okay, of those days. And you can see it's an old paper, 1919, because it costs only 3 cents. What costs 3 cents today? I mean, what, my God. It says, eclipse shows space is limited. Greatest discovery in history. It was a big deal. Sir Oliver Lodge, and he was also a head honcho over there in Great Britain, calls discovery great triumph. And the New York Times, also put a little thing there. It says, lights all askew in the heavens, and essentially proved that Arthur Eddington, with his photographs of the eclipse, showed that light curves around the sun. Okay, or that's what he thinks he showed, because he was not a very smart individual, and so he just bought into Einstein's theory, and that created somewhat of a problem, because you had especially all these Germans who did not like Jews. People like Leonard, who was a Nobel Prize winner. So was Stark. And Stark was also a Nobel Prize winner, and they hated Jews. And so they began to use this term Jewish physics to anything that came out of Einstein, which later on was propagated to people like Niels Bohr, whose mother was Jewish, and other Jews, because they studied at universities. They were professors at universities, and they used this against that kind of reasoning. The fact that there is no ether, right? One, and the fact that they're using all these weird explanations to explain regular physics. So they said that's Jewish physics. And some people like Werner Heisenberg, who was not Jewish, was criticized quite a bit. He almost lost his positions also in Germany, because he was in favor of Jewish physics. The physics we have today, quantum mechanics and general relativity, those were considered Jewish physics. But that started in 1920. That's when Leonard, especially Philip Leonard, was somewhat of an important guy in Germany because of his Nobel Prize. And he said, look, this stuff has no place in physics, and so they were resistant to all this stuff. And what happened was Einstein's going to publish his book in 1917. He was still a nobody. He becomes a somebody in 1919, 2 years later, probably a little less, right, because of the months. And that's when Arthur Eddington blesses his theory. And that's when he becomes a household name. His name starts being synonymous with intelligence, and that's where Einstein starts growing. So that's the context that's happening out there. But Einstein at the same time could not fight against the people who were supporting him, because he was proposing that there is no ether, and that was against the belief, the religion of the mathematical establishment at that moment in time. So he had to kind of fit it in there, say, look, appease them, Finlandization, they call it. You have to appease these guys and say, look, there is an ether, but it's really space-time. And that's the way he put it. But they never resolved the issue with four-dimensional space-time or whatever. We need to know if there's a physical object called ether out there, if there's a medium called ether or not. Is there a physical object, a medium called space-time or not? And this is what we need to resolve, and they never resolved that, even to this day. They use it as a physical object, then they say it's a mathematical concept, and they, transfer this mathematical concept and use it as a physical object. And when you question that, they say, well, that's philosophy. You're taking the analogy too literally, and we have to answer how the Earth doesn't fly out of the solar system. Why does the moon get out of the solar system? And they say, well, it's warp space. Well, that's a physical interpretation. Yeah, we're trying to interpret our equations, but we don't understand Father Universe, and we don't have to speak the same language as Father Universe. But the language of Father Universe is math. We understand the math, and this is the best we can do to translate that math into regular language. And that's the situation today. Okay, and so we have what happened was, Einstein replaced Newton, partly because of an issue of precision, of accuracy. They say that Einstein's equation is more accurate than Newton's. It could explain Mercury's perihelion a little better, just a tiny bit, but that wasn't really the reason. The real underlying reason was that Einstein provided a different physical interpretation to gravity than Newton. Newton essentially said, look, there are particles. He was a particle man, but I mean a real particle, corpuscles, not quantum particles, okay? He was thinking in particles. He was thinking really in terms of what we call gravitons today. And he said, look, the sun attracts the earth, and he was thinking of particles, but he couldn't make them work because you can't attract with particles. And so he says, I have no hypothesis. Fingo non hypothesis, he said in Latin. He had no way of explaining that. And Einstein, and nobody had until Einstein came along. Einstein said, no, because there are no particles. There is not a force. What you have is the bending of space-time. Gravity is geometry. And what you have is the bending of space-time, and the Earth rolls around the sun and the moon around the Earth because space-time is warped. And that's a mathematical it's a physical interpretation of the mathematics. That's what they interpret, that what is being bent is space-time. You have to assign physical properties to this abstraction, this mathematical abstraction. And when you say, well, that's irrational, they say, well, you're taking the analogy too literally. Or we don't do that kind of work anyway. We're trying to explain it as best we can, what our equations mean to us, and we're trying to give that to the public. And so if we have to illustrate it, that's what they illustrate. Okay, so that's the situation. The situation is either we go with Newton or we go with Einstein. And part of the problem here is that in the case of Einstein, his theory doesn't work. Okay, it really doesn't work. They never tell you that it doesn't work, but it doesn't work. Here, let me give you a couple scenarios. One is a rocket in space, right? And it violates Newton's third law. Okay, here it is. And, Newton's third law of motion says for every action, there is an equal and opposite reaction. When a rocket goes through space, right, it doesn't push against space. A lot of flat earthers don't understand that. And it takes a long time to educate them. Anyways, a propellant moves backwards, right? And it automatically gives an impulse to the rocket going forward. So there is no push against space. So Newton's third law of motion, right, shows that that space is nothing because you're not pushing against space. I mean, it would be much easier for the people at NASA, for example, when the rocket leaves the Earth, it pushes against the ground. No problem. Everybody understands that. Push against the ground, goes upward, right? But in space, it doesn't push against the anything. The thrusters simply push outwards, and by pushing outwards, the rocket moves forward. Okay, that's how a rocket works in space. And it works with Newton's third law, and that violates Einstein's special space-time. Why? Because if space-time were a physical object, right, you could push against space-time and move forward. You wouldn't have to use Newton's third law. Okay, that's the first problem. The second problem is this one, okay, and that's a violation of Newton's first law, and that is that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. What does that mean? It means that here you have these rockets, and the people in NASA, they don't factor that rocket is moving through molasses or through an ocean or through air. No, it's moving through nothing. Because if they had to factor that there's resistance from some kind of medium called space-time, where you have this molasses, this water, whatever medium you want to think of, this fluid out there, ether, right? Then it would have friction. And, they don't calculate that. They don't factor that when they send a rocket out into space. So the rocket not only violates Newton's first law, but also third law, right? Both laws are violated because, in the sense that it shows that there is no space-time, because you don't push against space-time, and space-time doesn't cause friction on your spaceship, meaning that, it travels in a straight line like if there was nothing there, which is exactly what is out there. Nothing. That's what space is. That's the region between the Earth and the moon. It's called nothing. Okay? Nothing is that which has no shape, and it has no physical properties. But Einstein had to put some in there. Okay, so here's one fellow, and he writes the following. It says, I have an analog with boats throwing balls to each other and transferring momentum for repulsion and boomerangs for attraction. So he's going to explain Newton's force law using these notions. And if Newton would have found out about this, maybe he could have challenged Einstein if he came around, right? Saying, no, I do have a mechanism. I'm sorry, I thought I had none, but I do. And this enlightens Newton, right? He says, momentum conservation directly for the repulsive, angular momentum conservation in the attractive. As all analogs, it should not be stressed too much. And yeah, you have to really stretch his interpretation, and I'm going to illustrate that here in a second. Here's his boomerang theory compared to his repulsive one. Repulsive one we all understand, with particles, hitting against each other, pushing each other away. The boomerang one is the one that's very interesting. And here it is. Okay, when the pitcher throws a ball, the pitchers move backwards, right? So you throw a ball or you throw something, for example, heavy, right, forward, you move backwards, right? We all understand that. And the person catching also moves backward because, you're receiving this mass, this rock, this ball, whatever, and you're pushed backwards. So both persons are pushed away from each other. We all understand repulsion. In fact, all you need to do is throw a ball against another ball. You'll see that they'll bounce away. But look at the boomerang theory. Throws the boomerang, and because you throw, you move backwards. No problem there. So far, so good. But the boomerang goes around and pushes the other person backwards. So that's the boomerang theory, okay? If Newton only would have known all that, he could have challenged Einstein. So, now you know the boomerang theory. And here you have the typical one that they use out there. Again, it's beyond comprehension. It's known as negative momentum. I use the quarks here and the gluons, but it can work for gravity as well. If you are talking about two objects, the quarks being two objects, mass, right? And you have something in between them, a little particle that's going back and forth. One shoots the particle at the other object. How does it attract it? That's the question. And they call it negative momentum. Why? Because all you have to do in math is put a negative sign in front of momentum, the little p, right? And suddenly you have attraction. So mathematically, yes, it can be done. Or like we used to say in engineering, you can, with math, you can prove that an elephant dances upon a pin. And that's more or less the situation there. Yeah, you can prove anything with that. Okay, so because of Newton's theory, right, of particles and his mass divided by distance squared, right, if the sun were to disappear, right, the Earth would be flying out instantly. There would be no time delay. Sun disappears, the magician comes, makes the sun disappear. Our Earth would go flying out immediately because of the mass distance squared equation, right? So it would look something like this. May not start at the beginning. Let's see. Okay, here it goes. Here's the sun, right? Now we're going to make the sun disappear, okay? And look what happens to the Earth that's rolling around there. Here it comes. Bleep. There he goes. You can see what happens to the Earth. It goes flying out of the solar system immediately, okay? So the Earth would receive the message instantaneously. That's what I'm showing there, okay? And here is Einstein's version, okay? And again, in this case, it takes 8 minutes, according to Einstein, because the speed of light is 300,000 kilometers per second, and nothing can travel faster than the speed of light, including gravity. That means that if the sun were to disappear, we would not find out about that until 8 minutes later, when both light and gravity arrives at our light arrives at our eyes, and gravity comes at the same time as a feeling. We feel that suddenly we lost gravity. Okay, here it is. Okay, here's the Earth going around the sun, and suddenly, the Earth, the sun disappeared there. Here, you'll see it from the beginning in a second here. It's a GIF. So here's the Earth going around the sun, and it disappears. And so what does the Earth do? Well, it goes flying out 8 minutes later, okay? Because that's how fast light is. It cannot move instantaneously. So they have this idea that, the light and gravity both travel at the same speed, okay? Which is total nonsense because of what I said earlier, and that is that weight is location specific. It's a static concept. What does that mean in this context here? It means that you have weight for a given location in space, okay? So it doesn't matter where you are around the Earth, you already have weight, whether you put yourself on a scale or not. We don't care about measurement here, okay? You already have weight. And at different locations, location being a static concept, the astronaut already has weight. And if we have weight with respect to the Earth, and likewise the Earth has weight with respect to the sun. If the sun were to disappear, we're missing one of the masses. Mass, distance squared. You erase one of the masses, well, now you don't have any gravity, because that's what it was, a separation between two objects. You make one object disappear, the other one has no mass. Okay, if we removed all the objects in the universe, right? And we only leave the sun and the Earth, and you make the sun disappear, what gravity does the Earth have with respect to what? That's the issue. Okay, you need that mass distance in the denominator. And so, this notion that it takes gravity 8 minutes to reach you when the sun disappears, absolute nonsense, poppycock. Okay. Anyways, I have more material, but the rest of the material I'm going to have to leave for next week. I was hoping to cover it all today, but no way. I'm going to have to make it a part 2. Okay, so we'll see you next Sunday with following up on this same